Hello there, welcome back to our channel, and we are discussing the topic of multi-stage or cascade amplifiers. So we require a multi-stage amplifiers in a situation where a gain provided by a single stage amplifier is not high enough to be used in a specific application. You want more gain, and because of that we have to use multi-stage or cascading of the amplifiers. And second reason that we go for usage of multi-stage amplifier is the fact of impedance mismatch. So for example, you have this voltage amplifier implemented by a common emitter stage consisting of transistor Q1, RC, RE, R2, and R1, and C1. And here I have to place another capacitor, that is coupling capacitor C2, that makes up the common emitter amplifier. And this amplifier is known for its enough high input impedance and moderate output impedance. So in a case where you require so this is a voltage amplifier, and the ideal characteristics of the voltage amplifier is that it has a very high input impedance and very low output impedance. That means if it has a very high input impedance, then this amplifier requires a lowest possible current to be driven by an external voltage source. And if the voltage amplifier has low enough output impedance, it means it has the capability to supply any amount of current that is required by the load. But in a cases, for example, this is a common emitter stage, the input impedance of this amplifier isn't high enough, ideally, or it is high enough, and that's why we are using the external voltage source to drive it. However, its output impedance is not low enough to be uh, able to supply a high demand of current required by the loads. So in such case, we need to put up another amplification stage, which may not or may provide another gain factor. And the combined gain of the multi-stage amplifier in that case will be gain of stage 1 multiplied by the gain of stage 2. But in this case, as you can see, the second stage is composed of the common collector or emitter follower, also known as emitter follower configuration, which has a gain of less than 1 or approximately equal to 1. However, this stage addition provides us the low the lowest possible output impedance, which is not possible by using only single stage common emitter stage. So the combined input impedance and output impedance of the multi-stage amplifier would be such that here the input impedance offered by the common emitter will be high enough, and the output impedance of the multi-stage amplifier offered by this voltage buffer will be low enough to satisfy the impedance matching requirement in a signal chain. So the output of the first stage is becoming here an input of the second stage. And that's the final output. So we have seen this circuit in our previous module. We got the design of this amplifier in such a way that we use the transistors 2 and 2222. This is the general purpose small signal amplification transistor, where we set the gain of the common emitter amplifier is set by the ratio of resistor RC divided by the resistor RE. And this circuit is potentially uninfluenced by the intrinsic parameter variations of the transistor, which can vary due to the temperature effect. For example, the transconductance of the transistor is a function of temperature. So putting the emitter resistance, which is also called as emitter degeneration resistance, helps us to get rid of the transconductance involvement in the final gain expression. Without RE, we have a gain output will be minus GM times RC, and with RE, we have the output will be equal to uh, gain times the input, and the gain is set by the ratio of resistor RC and RE. So you don't really have any dependence of gain over the temperature here. It is independent of it. And so we chose the values of the resistance and the capacitances. For example, resistances are chosen here in such a way that the potential VB is applied to the base, and the voltage at the collector and the voltage at the emitter is also set by the proper resistor ratios, and which also gives us the gain. So gain based on the value of RC and RE here is about 5 times the input, 5 times. So the output, in other words, the output will be 5 times greater than the input. Okay. And the values of the capacitances C1 and here we need the C2 are chosen in such a way that their capacitances are high enough at the desired signal frequency of operation, so that the reactances at the required frequency will be minimum. So they acts as a they acts as an AC short at the signal frequency of operation. Okay. So with those values, we've got covered the DC operating point analysis of this transistor circuit, and we've got the we made sure that the transistor operates in the linear active region, and then we ran the transient or time domain simulations. Then we ran the AC or frequency response of this circuit. So if you are new to this episode, do refer back to those elements which are given here in our channel. Now we are going to replace the second stage because sometimes I need to design an AC coupled amplifier, AC coupled using common emitter stages. So what I will do, I will have the same circuit of the common emitter as a second stage. So I will replace that. Maybe it's my choice to put up third stage for again the impedance matching purpose using the voltage buffer as a third stage. But right now I'm going to delete this stage and add up this stage right here and see the complete response. So let me show you that step by step. You can see now, let me delete this part of the circuit, which I will do it right now. Okay, so right now we have completed our circuit. So here you can see is the complete multi-stage amplifier. It is called as AC coupled amplifier. And because I'm using capacitors to couple the signals, for example, input signal to the amplifier stage, and here the output of the first stage to the input of the second stage, I'm again using a capacitor here. So that's why it is called as AC coupled, and it's also called as AC coupled common emitter stages. So it is possible to create this multi-stage cascade where each stage, as you can see, is separately biased, and it's coupled to adjacent stages via DC blocking capacitors. Okay, so inserting the coupling capacitor between the stages blocks the DC operating point bias level of one stage from affecting the DC operating point of the next. So my capacitances are helping me with that. So, however, the resulting overall amplifier can no longer respond to DC or very low frequency input. The capacitances, which are called as coupling capacitances here, which are, for example, they are used here to indicate that their capacitances have been chosen in such a way that the values are large enough at the specified signal frequency to have negligible reactance, and then therefore they can be treated as an AC short circuit. Okay. So it is also useful to note at this point that the method of including the capacitors across the emitter degeneration resistors to increase the gain at the higher frequencies can be employed in case of these multi-stage amplifiers, as well as single stage amplifiers also, right? So we are basically using these capacitors across emitter degeneration resistors to increase the gain at higher frequencies. Now, let me add one more capacitance here because I have to do that. So before that, I will just click here and then press F6, which is helping me to duplicate the component, and then I'll place it here. Again, I will use the wire to connect this circuit. Now, the first thing first, what I would like to do is to run the operating point analysis and to make sure whether these transistors, which are the similar type of transistors, if they are biased in active region or not. So for the DC analysis, we'll use the .op command here. I have to use it only once. So you can see there is 2 times now. So I will just remove one. And now I will save it and then I will say simulate, but I have to before that disable this AC command here also. So what I'll do, I will right click on this and here I will put this semicolon and then click OK. With that, the transient and the AC analysis is disabled for a moment, and the only analysis I am running is the dot operating point analysis. So let me show you what is the result of performing this analysis on this circuit, which is the AC coupled amplifier using common emitter stages. I will click run and look at this table now. So here it gives me the voltage VO, which is biased, the DC bias level of this node is 6.22 volt. The VB is here, which is biased at 1.75. Then I have these other nets, N005 and 001 is 12. So obviously that's the supply voltage of the circuit. And N003 is 0. So I have to verify what net is that. So I haven't labeled many other nets, but most important thing, I want to just ensure in which region my transistor is biased. Okay. So this is V of V out. So it is nearly 0. It's like microvolt, as you can see there. You can see that. So let me show you that what we can do with that. Okay, just a minute. So I have rerun the analysis by doing some labeling function here. What I have done is that I have labeled the nets at the collector. I said this node is my VC2, that is the voltage at the collector 2, transistor 2. This node is the VB2, that is the voltage at the base of transistor 2. This node is VE2, that's the voltage at the emitter of transistor 2. And so is the voltage at the collector of transistor 1 will be VO. The voltage at the base of the transistor 1 will be VB1, and the voltage at the emitter of transistor Q1 is VE1. So here we go. See, VO is 6.22, that is here. VB1 is 1.75. We want this collector to base junction to be reverse bias in order to have transistor in Q1 in the active region. Base emitter junction should be forward bias. So let's see that by seeing the DC bias level at the pins of the transistors, collector, emitter, and the base. So VO is 6.22, VB1 is 1.75. So the difference here is about 4.25. So obviously the voltage at the collector is much greater than the VBE of the transistor Q1. But what is VBE? Let's do that. So VB1 is 1.75, VE1 is 1.06. So approximately this seems to be in a forward bias. The voltage difference here is about 0.66 volt. Okay, so that is 660 millivolt. That's this thing. Next, we can come back here and see what is VC2, VB2, etc. So VC2 is 6.2 volt, VB2 is 1.7 volt, same as before. And our VE2 will be 1.06, same as before. So again, this transistor have the same biasing and operating point right here. What is the voltage at the collector? That is, we just said 6.2 to halfway of the mid power supply. And then you have a V out, which is at the 0 volt. That's the DC bias level. Okay, and collector current now is 4 milliampere through the transistor 1. Base current is about 23 microampere. The beta is about 200, which is also verified from the SPICE nest list. The collector emitter current is 4 milliampere approximately. And the same story is for transistor Q2. That is the one. So we got this DC operating point, ensuring that the transistors are biased in the uh, proper operation in the active region or the linear region. Okay, the currents are constant through the collector to emitter of both the transistors. Now the combined gain of this multi-stage amplifier would be gain of the first stage multiplied by the gain of second stage. The gain of the first stage theoretical is RC divided by RE, which is approximately 5 times, which is approximately 5 times, and which is approximately 5. So it means the output will be 5 times higher than the input, and then therefore we see that we can actually have this one. So what we see that the combined gain here will be gain of 5 from the first stage multiplied by the gain of 5 from the second stage. So we should have 25 is the total gain, 5 times 5. It means the final output would be 25 times the input that we apply to the circuit, which is AC coupled emitter, using common emitter stages. Okay, and this is a multi-stage or cascade amplifier. So let's simulate the performance of this circuit. So I will right click this input AC voltage source. I will choose that I want to apply a sine wave. Then the AC amplitude is not required for now because I'm using the time domain simulation. DC offset will be set to 0. I don't need a special DC voltage here because the resistor R1 and R2 in both these stages are a bias circuit that is setting up a base voltage of the transistor, which is helping me to set the bias point. Amplitude is, let's say, 10 millivolts. So it means the output should be 25 times that. That is 250 millivolt peak I should have at the output. And frequency, let's say 1K. And I want, let's say, 10 cycles. I will click OK. Now I have provided a sine wave source that I place somewhere here, let's say, and space, and then I will reopen my time domain analysis. So I will just go to time, right click on the time domain SPICE syntax. I will remove this semicolon. I will just click OK, and that's it. This analysis is now enabled. With that, I am going to save the file and click on run. And look at our input waveform, look at the schematic. I am going to click the probe, and therefore I see that I have now AC sine wave. that I have clearly seen from the screen. And now I want to plot the output signal. With the input plotted, now I want to pay attention to plotting the output of the first stage. So I got back my mouse. I'm hovering the mouse on the schematic portion of the screen, and then there is a red probe, and I will click on this. And look at this, output is in the blue. Now I will right click on the waveform and click zoom to fit. So I am barely able to see that. So I will add plot pane and then take the input up and the output down. So obviously my output is inverted form of input because it's the inverting amplifier, and the DC bias level of the input is 0 and it is going to 10 millivolt. The DC bias level of the output is about 6.21 9 or 6.2 something, and then I have this peak value attempting. So let me count how much is the gain. So it is like starting from 6.2 3, and it is going to 6.175. So it's about 5 times output I have, because the DC bias level is like that. So it's not much clear from this time domain analysis, but with the AC, uh, with the AC or frequency analysis, we know that the gain is magnitude of the gain is 25, and in decibels we will have 20 log of the magnitude in dB decibel. So we'll see that. But now I have got this zoom to fit, and on the right only I am going to plot the final output. So look at this is the red one. Again, my views are not clear, so I will add a plot pane, and then let's say V input goes here, the output of the first stage is here in the middle, and then output of the second stage. Again, see now your output is in the final stage is inverted, and it is in the same form of the inputs. Okay, for the positive half you have positive half, for the negative half you have negative half. There is a little bit phase difference between the input and the output. That is due to the capacitors that have been placed here. Now how much is my output here? So you see, for example, I'm starting with the 0, and let me zoom in this portion. For example, this is like 35 millivolt, and this is like the peak value, or the peak value is like how much is that? So right click again here, zoom to fit. So the DC level of this signal is about 25 millivolt, and the peak value is going to 250 millivolt. So I guess for the 10 millivolt input, I have about 125 millivolts. So it's about 12.5 times, or in one way, or it's about 25 times. Let me check that out. So approximately you have like from 0, you go up to 250 millivolt, right? And for upper level would be about from about 25. So you are getting 200. So you can see that the output is about 12.5 times higher than the input signal, right? So that's how you can actually design this multi-stage amplifier. Now the final analysis that we are going to run is the AC analysis. So let's close this. Let us tile the windows and press spacebar on the screen. Your circuit schematic is visible again. Now I will enable, by right clicking on this analysis, the AC analysis. I will click OK, and then I will disable, or even if I don't do that and directly run the simulation, the simulator will ask me which analysis I want to run. So I want to run the AC analysis, but before that I forgot to change the nature of the voltage source. So I will right click here, I will click none, and the AC amplitude is the small signal AC analysis. So I will set AC amplitude to be 1. I will click OK. AC voltage source has been set up there. So as you can see right now here, and then I will run the simulation. It is asking me to choose. I will choose the analysis about the frequency response. I will click OK, and it plots me the output. Now look at the first stage amplifier output. The gain is constant here. Then you have like band pass response in the middle. Our signal frequencies of interest for which you want the required gain. So for frequencies from approximately DC to about 1 kilohertz, you have a flat gain of 10 dB. Then you have a gain of 35 dB for the frequency about 100 200 kilohertz to 300 kilohertz. How about we got to plot the final output? So again, obviously you can see the gain is doubled, and the gain is now about 25 dB, which is like you can see that how much is the gain for the blue. Yeah, it is 25 dB for the frequency of about 1 kilohertz. Okay, and then again your gain is doubled here, and that's how you can actually. So how much is 20 log of what value is your 25 dB? That needs to be answered, and that is your conclusion from this. So let me do that. So in conclusion, you can see that it is about 25 dB, and that is 20 log of 25, right? That value is there. You can right click here and choose the linear instead of decibel and click OK. And now look at this. You can right click again, zoom to fit, and you actually can see how much is your gain there, but it is not giving you on the linear scale. Okay, because it is really barely seen there, so it's really not coming up. Okay, so better you just right click and plot decibel, and that's it, and zoom to fit. But look at the phase for the green dotted line. The phase at the desired signal frequency where the gain is constant is about to minus 180 degree, which is due to this uh, first stage of inversion. And for the second blue curves, the gain is here constant uh, about 0 degree, right? So right here, that's pretty well, because at the output of the first stage, your signal is 180 degree phase shifted to the input, and the output of the second stage, your signal is in phase with the input. So that's all. So this is the story of the multi-stage amplifier using common emitter stages. Hope you like this, enjoyed this, and put some comment, like the video, and share with others. Stay tuned. Wish you happy learning.